Welcome to the MRS tutorial on predicting phonon densities of states with Euclidean neural networks. This part of the tutorial is presented by Nina Andrejevic and Zhantao Chen from MIT. The phonon density of states, or the number of phonon modes with a particular vibrational frequency, arises in the calculation of many fundamental thermal properties, for example, the lattice heat capacity, and by extension, the thermal conductivity. It also plays a key role in interfacial thermal transport, where the overlap of the phonon densities of states of two adjacent materials determines the energy propagation by phonons of a certain frequency. Finally, the phonon density of states influences the critical temperature in phonon-mediated superconductivity. Despite its ubiquity in thermal and electronic transport calculations, the phonon density of states is non-trivial to obtain. It can be measured experimentally by inelastic neutron or X-ray scattering, which are limited resources available at scientific user facilities. On the other hand, ab initio calculations scale rapidly with the number of atoms in the structure, incurring a high computational cost for large systems, especially disordered structures. Finally, data-driven methods face the challenge of currently limited databases of phonon densities of states available, with only 1 to 2,000 examples. This further makes it challenging to learn a comparatively high-dimensional output such as the density of states, which is a function of energy. Additionally, since crystalline symmetry is a key determinant of the phonon dispersion, encoding crystal structures is necessary, but simply using atomic coordinates means extensive data augmentation is needed to capture arbitrary rotations of crystal structures. In an effort to overcome some of these challenges, we used Euclidean neural networks to directly predict phonon density of states from crystal structures and atomic masses. Since Euclidean neural networks are symmetry-aware, no data augmentation is required to fully encode the crystalline symmetry. e3nns are also by design equivariant to 3D translations, rotations, and inversion. In addition to capturing relevant physics, this property constrains the space of functions over which we optimize during training, making it easier to train networks with more limited amounts of training data. Finally, we'll show that our implementation extends naturally to systems with substitutional disorder with no added computational cost.
In this tutorial, we will walk you through several key steps in predicting phonon density of states with Euclidean neural network. We will start with building periodic graphs from crystal structures. In particular, each atom becomes the node of a graph and carries the feature representation of dimension 118 times 0e. Basically, it's an ordered array of 118 scalars. For a specific atom and with atomic number z, we put its atomic mass at the zth one of the 118 scalars and assign the rest scalars to be 0. The edges of the graph are formed between pairs of atoms with their relative distance r smaller than a certain prescribed critical value, say the Rmax. Since crystal structures are periodic, to include this periodicity in the graph, we can simply allow the formation of edges between the atom and its periodic neighbors images at nearby unit cells as long as the distance condition is satisfied. We will then provide a clear visualization about the architecture of our e3nn based model and explain what mathematical operations have been done to the initial representations. Specifically, we will introduce the embedding of raw input for a more compact representation, convolution to aggregate local environment information and update the feature representation of each node, and the gated blocks to serve as nonlinear activations. Apart from the neural network itself, we would like to briefly discuss the results, provide some insights, for example, what the intermediate representations look like in real space, and we will also discuss some generalizations. In particular, we will demonstrate the capacity of predicting partial density of state, namely the density of state of each element, even though we do not train our neural network to do so explicitly. We will also go through the process of building n-hot input representations for predicting substitutional alloys. For example, if the same position or node can be occupied by 2 or more species with some percentage, then the feature representation of that node will have 2 or more non-zero components, with each component being the percentage times the corresponding atomic mass. Before we go to the hands-on part, we would also like to mention some considerations. Firstly, we note the periodicity in the graphs does not change the model. What it changes is only the input graph, as we just mentioned in the last slide that we allow edges between the atoms and their periodic images to be formed as long as this distance condition is satisfied. So this process can be schematically illustrated by this figure here. Specifically, those self-loops actually comes from the atom and the connection between atom and their images. The second consideration is that we always need to properly normalize our convolution, namely by dividing the convolution results by the square root of average number of neighbors z. So we should be careful that this z is typically dependent on your choice of Rmax. So after you decide what Rmax you want to use and build all those graphs, you always want to check what is the statistics of your graphs look like. And for example, by as shown by this histogram, and get an estimated z before you go to the prediction chaining and the prediction sections. The third consideration is that we want to mention the importance of the atomic mass weighted one-hot encoding. So we know that the phonon or lattice vibrational properties is closely related to not only their restoring forces but also the atomic masses. The former one can be learned by the neural network from the provided training data. And since we already know those atomic masses, why not we just tell the neural network and hopefully save some efforts. So this physical information helps the neural network to build connections between atomic masses and the density of states. And eventually this will help us to achieve better generalization to elements that has less or even no training data in the data set. Without further ado, let's move on to the hands-on part and play around with the code.
Welcome to the hands-on portion of the Phonon properties tutorial. This part of the tutorial will walk you through the code used to build and train a Euclidean neural network to predict the phonon density of states from a material's crystal structure and the atomic masses of its constituent atoms. You can access the tutorial materials from our e3nn tutorial MRS homepage. So just click on Phonon properties here, and then click on the link to the code here. This will take you to the GitHub repository for the phonon density of states tutorial. This tutorial is presented as an interactive notebook. So there are two options for interacting with the code here. First, you can either run it in a Google Colaboratory, which is good if you want to train your network on a GPU if you don't have access to one locally. Or you can work from a local installation, and there are the instructions here on how to get a copy of the code and install all the necessary packages. At the bottom, we've also included some references if you're interested in looking at any topics in more detail. For the walkthrough of the code here, we're going to be working from the Colab notebook, but this closely parallels what you would do working from a local installation. So the first thing we're going to do once we've loaded the notebook is to go to the runtime and select change runtime type and ensure that we have GPU selected. and then hit save. Next, we will clone the GitHub repo to access all the tutorial files. So to execute a cell, you can either hit the play button over here, or you can press Shift and Enter together. Once this is done, we're going to see a green check mark appear to the left here. And now we can move to the next step, which is to just install some relevant packages. This should take less than a minute. What we're doing here is to just install relevant packages like the ACE package, which is what we will use to save our crystal structure data, e3nn, which contains all the relevant functions for building our neural network, as well as some torch packages for handling graph-based neural networks. So once that's done, we're now ready to start the tutorial. So first we want to import all the packages that we need to use. And then the first thing we want to do is familiarize ourselves with our training data. So our training data comes from this database of DFPT calculated Phonon densities of states, which contains approximately 1,500 crystalline compounds. So in this next cell, we're going to load our data as a pandas data frame, and we display the first 5 rows, which have columns for things like the materials project ID, the structure, the phonon frequencies at which the phonon density of states is evaluated, and the phonon density of states. These are the main things that we'll need to train our model. But we also have included some additional columns, such as the partial phonon density of states for each element in the compound, which we'll revisit later when we go ahead and analyze our results. And then we also just have the formula and the species in the structure. The crystal structure in the structure column is stored as an ACE, or atomic simulation environment, atoms object. And these basically store the atomic species and positions of each atom in one unit cell of the material, as well as the lattice vectors of the unit cell. So this cell below is going to just plot the unit cell of the ith example in our data set, just so we get a sense of what they look like. So one property of our data that we care about are the relative distances between the atoms. As we saw in the introduction, our inputs are comprised of graphs, with the atoms represented by nodes and edges drawn between any 2 atoms within a certain cutoff radius. And so to help us determine a reasonable cutoff, what we can do is plot the statistics of the lattice parameters to give us a preliminary estimate. So that's what the following cell will do. And here we can see that the average lattice parameters in the A, B, and C directions are somewhere around 5 and 6. So next, we are ready to build our input features. The process here closely follows a portion of the e3nn documentation, which is linked here, and shows you how to handle inputs with periodic boundaries. So for each atom in our unit cell, we are going to associate a feature vector which one hot encodes its atomic mass in the index corresponding to its atomic number. As mentioned before, the unit cell is encoded as a graph in which the two different atoms are joined by an edge if they are within a certain cutoff radius called R max of one another. So the first cell here is going to build 2 tensors, one for one hot encoding the atom type and one for one hot encoding the atomic mass. Then the following cell defines the function build data, which will turn the structure of each entry in the data frame into a torch geometric data object that can be passed to the network. And this data object contains several fields, as you will see below, which are computed in this function. So first, we will pull out the list of atomic species, which are called symbols in our structure, as well as their positions, and also get a 3x3 matrix of the lattice vectors of the unit cell. Then we need to construct the crystal graph by identifying all the atoms within a distance R max as neighbors. Note that the neighbor list function that we're using to do this defines its cutoff as twice what our definition of R max is. And so that's why we plug in R max divided by 2 here. We're also setting the self-interaction parameter to true to ask that each atom has a self loop or an edge with itself. And this gives us 3 lists: edge source, edge destination, and edge shift. The edge source and edge destination are going to give us the indices of atom pairs that are joined by an edge. And the edge shift will give us the lattice vector shift of the neighbor atom if it's in an image of the unit cell, and is otherwise going to be just a 0 vector. And so with these lists, we can now construct the displacement vector between any 2 atoms joined by an edge, which we call edge vec. Finally, we can also compute the edge lengths, which are rounded here because we simply use these for plotting purposes, which we'll show later. And so all of these properties that we've calculated are then saved as fields of the torch geometric data object. And I want to highlight 3 additional fields in this object. In particular, the field X is containing our 1 hot encoded atomic masses. These are the node features that we're going to operate on with the equivariant convolutions. We also have a field Z here, which stores just the 1 hot encoded atom type. This field is considered a node attribute, which is a property that we want to associate with the node at each layer. So it's quite similar to the handling of the edge vec, which are the edge attributes. And their values are not updated at each layer the way that node features are. And then finally, we have the output, which is abbreviated PHDOS. And notice that all of these have been converted into torch tensors. And where needed, we have also used the unsqueeze function to add a batch dimension as the first dimension of our tensor. So in this example, we've chosen an R max of 7 angstroms, and then we'll apply build data to each entry of our data frame by executing this cell. Once we have this completed, it's nice to plot out some crystal structures again alongside the crystal graph representations that we've built. So that's what's done in the next cell. So this is the example we saw earlier, and this is the corresponding crystal graph. The plot is using the edge lengths to annotate the edges drawn between 2 atoms, and the nodes are labeled according to the atom type. We can vary this index to plot another unique example. Okay. So next, now that we've prepared the inputs and outputs to our network, we can divide the examples among the training, validation, and testing sets. And since we don't have very many examples, we've written a function here that's going to balance the representation of different elements as we do the train valid test split. And we are setting aside 10% for the validation and 10% for testing. As you can see in the plot, it's doing its best to ensure that the representation of different elements is balanced, but in certain cases where we have too few examples, they are predominantly allocated to the training set. So you can generally use this function to generate different partitions of the data using different random seeds. But for the purposes of evaluating an example trained model later on in this tutorial, we're just going to read in the indices of the corresponding training, validation, and test sets that we've prepared and used for training. And here in this cell, we're also setting up our data loaders, which are breaking up the data sets into batches. And again, since we have very few examples, we're just going to set our batch size to 1. The final step of preparing our data is to then calculate the average number of nearest neighbors, which are necessary to properly normalize the convolutions. And that's what's done in this cell. We will use the calculated average nearest neighbors and train from the training set in order to normalize our convolutions.
Now let us define the neural network. So this code block basically defines the class of model that we want to use, which is built on top of the network described in the documentation. And the key function is defined here, which is composed of 3 parts. The first part is the further embedding of our one-hot encoding. And the second part is is using the Euclidean neural network, namely those convolutional layers and the gated blocks to further process the inputs errors. And the third part is is asking whether you want to get partial density of states or total density of states and do some normalizations before output something. So the next code block here, we define some important dimensions inside the neural network. The output dimension is basically what is the length of your filtered density of states, and it also defines the final output of the model. The embedding dimension is simply what is the multiplicity you want to throw into the Euclidean neural network. And remember that our one-hot encoding is actually of length 118, and the transition from 118 to this 64 is done by the fully connected neural network. And of course, this embedding dimension also defines the irreps of your input and your node attributes, which is used to do some tensor product inside the convolutional layer. And this layer number equal to 2 basically means you will have 3 convolutional layers with 2 gated blocks sitting in between. And this multiplicity equal to 32 means is the multiplicity of your second and the third convolutional layer. And this error max equal to 1 basically defines the maximum degree of your spherical harmonics filters. And this maximum radius is whatever the cutoff radius that you have used above to to construct those graphs. And this number of neighbors is necessary, as we discussed in the introduction slides, to normalize your convolutional results. So, okay. So here we can visualize, actually we can visualize what is going on inside the network. For example, here we are plotting all those tensor products. This 64 times 0e is the embedded data.x, and this same dimension of irrep, but it's actually data.z, the embedded one-hot encoding. And we ask them to perform a tensor product and resulting some irreps that goes to the gates. So this is the first branching, and the second branch actually composed of all these three tensor products. Firstly, we also perform tensor products between the embedded data.x and the embedded data.z. The resulting irrep goes to the tensor product, this TP, where we perform tensor product between this 64 times 0e with the spherical harmonics, with the features, actually the age attributes, and obtain another two irreps, which goes to the next tensor product defined here. So there are two things that I want to emphasize. Firstly, we notice that even though we asked for the output of 32 times 10, because our input irreps do not have AR equal to 1 features, there is actually no connection being formed. So this what we have asked here is left spare, and they only have zeros inside. But differently, since our filter here has AR equal to 1 features, the resulting reps actually can contain such features. And the second thing that I want to mention is that the first branch and the second branch, their outputs will go together to the gate, but before going to gate, their results actually get merged. So actually, for more details, you should definitely check out the code to see what is going on. Then we arrive at the chaining part. Firstly, we defined some optimizer, which is a add-on algorithm with weight decay. And we also define a scheduler so that we can gradually decrease our learning rate to prevent any oscillations when the when the loss gets low. And of course, we will chain our neural network with the loss mean squared error loss function. And here we just ask if any GPU is available. If it's available, we will use it. And we will create a run name based on the current time so that we can save our chained model. And here we set the model.pool equal to true so that we will get total density of states. And we can perform the training with this chain function. Let us just see how it goes. So we can see the chaining is going on, and it's not very, the waiting time is not very long for one epoch, but we will not wait here to see the final chaining result. Let us jump directly to a pre-trained model, and we will start as shown here. And we will then start discuss some of its results and other generalizations.
Now we can evaluate a trained model on our data. So here we've loaded a pre-trained model and we'll apply it to all of our training, validation, and testing examples and get the predicted phonon density of states. And in the meantime, we'll also compute the mean squared error between the prediction and the ground truth. And then in the next 3 cells, we will then plot some examples of the reconstructions. So in all 3 plots, each of these small subplots shows the ground truth phonon density of states in black, overlaid with the predicted phonon density of states in the colored curve. And the subplot to the left shows the distribution of the data according to the error quartiles of the mean squared error. So this can give us sort of a visual look at how our model is performing. But one additional thing that's interesting to examine to better understand our model's performance is the node features right before they are aggregated together. So this can be thought of as a sort of learned signature of a particular atom that's determined by the model during training. So in this next cell, we're going to set the pool parameter to false in order to get the individual node features. And then the average of those for the same species will be plotted against the partial phonon density of states for the corresponding element. So in this plot, the leftmost column again shows our total phonon density of states for both the prediction and the ground truth. And the remaining columns show the partial phonon density of states in black, overlaid with the learned node feature for that element in the colored curve. And since the network wasn't explicitly trained to predict the partial phonon density of states, it's very interesting to see that there's actually some correspondence between those 2 quantities for many of the elements shown here.
So here we want to introduce the generalization of our model to predict phonon density of state for alloys. And in particular, we will predict the density of state for the magnesium bismuth or magnesium antimony system. So, okay, so firstly, from the data set, we want to get indices of the parent structures, namely the Mg3sp2 or Mg3 and Mg3bi2, so that we will get their structures, for example, the lattice constants, atomic positions, as well as the atomic masses, so that we can interpolate their values to obtain the corresponding alloy structures. And then in this code block, what we are doing is basically we want to create a series of alloy structures based on the percentage of bismuth. So this X bismuth is the percentage of bismuth ranging from essentially 0 to 1. And for each one of these percentages, we will do the interpolation on the using the PyTorch AirERP function to interpolate the atomic positions, their lattice constants, and of course the atomic masses and many others, as you will see in these code blocks. And then So essentially, we collect them all into this data underscore alloy. And then we can perform the prediction on this data sets composed of all kinds of alloy systems. And now we want to plot out those predictions. And in particular, here, in the left panel, what we are plotting is all those predicted density of states starting from the magnesium antimony system to the pure magnesium bismuth system. And an interesting feature to notice is the smooth transition as we gradually changing this bismuth percentage. In particular, you can see these wrinkles gradually disappear and the new wrinkles gradually appear. Of course, they may not correspond to real features in the dots of each parent system, but it's interesting to see those transitions. And you can imagine if we get better chain neural networks, we can sort of look at any percentage of any alloys with arbitrary percentages, as long as we can accurately predict their parent systems. And another thing that we want to mention is by considering by simply changing the input representations, we are not adding any other computational cost to our model. So they can be done, so these predictions are done as fast as those pure compounds. And in this figure, in the right panel, what we are looking at is the comparison between the predicted and the calculated density of states for the parent materials, as well as the alloy system calculated from the virtual crystal approximation. And we can see pretty good agreement between our predictions and the ab initio calculations. So now let us look at the visualization of learning intermediate features. In particular, we are looking at the intermediate features after the first convolutional layer and before the first gated block. In particular, here on the top panel, we are looking at some 0E features, which is simply scalar, so there's nothing interesting. And in the bottom panel, we are looking at the summation of some A equal to 0 features and A equal to 1 features. And because A equal to 1 features, you will have this sort of dipole. So you can see if some sites that have non-zero features will show this spherical harmonics, and those like disappearing sites simply means their corresponding features are zeros. So you can imagine that after each layer of operation, there will be similar things going on that you can always visualize them in the real space. So hopefully those visualization will be helpful for you to understand what is going on inside the Euclidean neural network.